Hello and welcome to the fourth lecture of the Brazilian ICPC Summer School 2022. In this lecture I'm going to talk about data structures, and in this lecture I won't be talking about very advanced data structures, things that are complicated or maybe have some very specific use. Instead, what I'm going to try to do is talk about simple data structures that you can use in many different situations that have a very general purpose and that you may know already, but I want you to think differently about them. So I want to stress that it's important to think in a certain way when you consider data structures, so that you are very quickly going to get the data structure that fits your needs, because you may know a few or many, but it's important to recognize when you actually need it. Then it's also important to know the inner workings of data structures so that you can know how to adapt them when some problem requires a specific change in a particular data structure. So this is what I want to talk about today. I hope that you learned something, and of course you can then go to books. There's many references and many places where you can read about more advanced things, but I think the basics are important. The basic thing is how to think about data structures in the context of ICPC and more generally competitive programming. So first things first, what's a data structure? A data structure is essentially one particular way to store data and to operate on that data. And the whole point is that you want to do this efficiently. So you want to store a certain type of data and operate with certain operations on it efficiently. So you can think of the data structure as a black box, which in principle you don't need to know what's inside that black box, but that black box will take some input and will produce some output, and it will guarantee that this takes at most O of something. So of course the time this operation takes depends on the input, but it's guaranteed to asymptotically grow with the input size in a certain way. Now, if you look at it this way, there really is no difference with any algorithm. So an algorithm takes an input, produces an output, and when you analyze the algorithm, you end up proving that it functions, it terminates in O of some function of n, the input size. So in principle, there is not a big difference between algorithms and data structures, in the sense that if you consider an algorithm to be a black box, maybe you can think of it is a data structure. So maybe one difference is that the data structure has some persistence to it, in the sense that it stores some data and then you can send many inputs. So you can send this can have an index, let's say, and it will produce many outputs, and there can be a correlation between the inputs and the outputs. There's also in data structures the possibility to have some initial state. Okay? Now, again, all of these things may be considered in algorithms. So it's not a clear-cut difference, but more of a practical difference. Algorithms are things that first you want to know what is inside. So you know the important thing is what's going on inside. So for data structures, you want to forget about it. Why? Because normally this is a much smaller problem. So you can think that your problem is some large thing which the algorithm is trying to solve, And inside of it, there's sub-problems, small things that need to be done. And of course, there might be some order, some interactions between them. But here, these small things, maybe they are small enough and they are common enough that you need them in many different algorithms. So in that case, you can say that this thing, this little part, will become a data structure, and you will use it as a black box. You will code it once, but then use it in many different algorithms, and it will be like a gear inside your bigger algorithm. So while you may have to design the solution of a problem, including many different parts, some of these parts may be things that you already solved before and that you know how to do, and you have some pre-prepared code that can do it, and this code is guaranteeing you some certain execution time. Again, you can think of algorithms in this way, and complex problems, maybe a complex graph problem will involve at some point computing a minimal distance from one node to the next, and you know many algorithms can do this. Or maybe some other problem requires computing the factorization of a number, and you know you can use some algorithm to find prime numbers and factorize natural numbers. So again, this practical difference is not clear cut, but in principle, you can think that data structures will be at a lower level, and they will be the bricks that you will use to construct higher level algorithms. So the goal of this lecture is, at least in part, to get you to be aware of the small problems, the sub-problems that appear when you solve a larger problem. Some of these have standard solutions which are implemented in data structures, and if you can recognize that, you will do much better and you will solve problems much faster. So the first example I will talk about is one you surely know or you have used. If you ever code in C or C++, I'm talking about sets. Now, if you code in Java, there might be an equivalent I don't know about. If you're coding in Python, in principle, Python sets are not quite like C++ sets. And here I'll talk more about C++, standard library sets. And in Python, there's equivalent things that you can do, but keep in mind that this is a data structure pre-implemented in the C++ standard library, but there's other equivalent data structures in whatever language you choose to code in. So the set is very simple. In C++, the set can be represented as a bag where you keep some elements. Let's call them A, B, C, and so on. And these elements in this bag are sorted. So sets in C++ are ordered, and it's like keeping a list of elements, only you always think about this list as not having any repetitions and being ordered. So sorted and without repetitions is the main. This is the main property of C++ sets. And what can you do with these sets? You can perform some operations, as I said. These operations include adding elements. So you can add an element. You can remove an element. And you can also find the first element that is greater than a given value. So you go over this list of values and you find the first one greater or greater than equal, depending on which function you use, than a given value that you have. So, as I said, the data structure should store some data, the elements here. It should provide some operations, and it should guarantee a running time. In this case, all of these operations are guaranteed to run in O log n time, where n is the number of elements. So you see, this is a very basic type of thing. You can find many problems where you will have to take care of a list of elements, check whether an element is there or not, add one, remove them, find one greater than some bound, etc. So this is a simple thing. If you go to a book, you will find the implementation of this data structure. So you will find an explanation of heaps and stuff like this. And you will see the many use cases that it can have, like priority queues and so on. But in principle, once you know that stuff, or even if you don't, you can use the set. So you can use this as a black box. Now, you can also bend the rules. So even if I said the set in C++ is sorted, and it allows you to find the first element greater than some number, for example, sometimes you don't need that, and you can do a bit better. You can then forget about finding elements larger than a given bound. You forget about having the elements sorted. Then you're looking into a different data structure, unordered set. And if you use this one, then the guarantee is that on average you get O1 time. So you see, the data structures with different capabilities will give you different running times. Therefore, knowing what you need to do is crucial to choosing the correct data structure to use. And even if you think the data structure does not satisfy your requirements, for example, you may have a list of elements, but you want to actually consider repetitions, then sometimes you can bend the rules and use a data structure in a non-typical way, in a non-standard way, to, you know, bend a bit its constraints and work anyway for your problem. So for example, to take care of repetitions, you could say you can drop this and just consider pairs of elements. So you take the element and you take some other label, which can be whatever you want, to distinguish identical elements. So you can create a set of pairs of things where the first one is the element that you have and the second one is a label. As long as you can compare these pairs, you will be okay. And then you have a multi-set or a set that can handle repetitions. Now, in this example, I want to stress the fact that you do not know how the set is implemented. So you really have a black box. If you actually go to the code of the standard library and you look at the code, it's probably some well-known studied algorithm, but it's highly optimized to fulfill its purpose in a very efficient and flexible way. So you don't know how the set works internally, and you don't care about how the set works internally. You only know the things that you can do and the things that you cannot do. So for example, in the set we said that one operation was add, add an element. Another operation was remove, to remove an element. But there was no operation to modify an element. In fact, if you modify an element that is inside the set, for example, you take a reference to it and you change it, you will break the data structure and you will probably get some runtime error. So you don't have a modify operation, and if you want to have a data structure that allows for modifying elements, what you have to do is essentially wrap this up in a different, in a new layer, where now to implement the modify function, you will also have the add and the remove. These will be connected directly, but modify can be just remove, then actually change the element, then add again. Now, because this is all log n happening on the underlying data structure, this is also log n on the underlying data structure. The whole running time is controlled by either O log n or OT, the time you take to modify the element. So you see, when you have a data structure, you can create higher level data structures out of it that allow for some operations that were not originally provided. I call this process layering of data structures, and it's one of the key things that I think will help you solve problems using data structures. So you will know some basic ones that you're very familiar with, and then combining them, wrapping them up in simple functions that perform combinations of their operations, you will be able to create many more advanced and more complicated data structures without actually writing a lot of code from scratch. This is one of the things that I think you should keep in mind when trying to solve problems using data structures. You don't need one tool that is pre-made to solve your problem or to solve even your sub-problem, but you need one tool that you can adapt and modify so that it actually does what you want. So, just for the sake of completeness, let's see how you use such a data structure. So consider, for example, that you have the plane with x and y coordinates, and you have some points in this plane, and you want to sort them according to the angle. So for example, this point here has a given angle there, and your algorithm requires you to do a sweep line, move a line going around the points according to their angle. Then you can simply define an order relation between points according to their angle with the x-axis, which is computed by the 8 and 2 function in C++. The points are stored in a very simple container for 2 numbers in C++, and then just keeping a set of points ordered according to the angle with the x-axis is all about just creating a set. And as you insert the points and maybe remove them, process them, whatever you want to do, these are always kept ordered according to some complicated ordering, in this case the angle. So you see, even if your algorithm may be doing something very complicated with these points, the bookkeeping part of keeping them ordered according to the angle is very simple. So this is the whole function of a data structure. Keep things simple as far as you can in your algorithm. Let the complication be the real operations that you're trying to do. Another example, Dijkstra's algorithm for finding shortest paths. In this case, we define a set of pairs where the first element is the distance to the source node, the second element is the current node or the node ID, and you just do the usual Dijkstra algorithm where you get from your set the currently closest node to the source, which has not been processed yet. So why am I showing this? Because I want you to think about the fact that some languages will simply provide a function to compute shortest paths in generic graphs, and you will never need to even know how it works inside. This function would be like a data structure, taking an input, a graph, and giving you as output the shortest distance from a given node to some other node. it would be, of course, better to think about this function as more like an algorithm than a data structure, because in particular, it wouldn't be storing any data. But you know, this is semantics. What's important is that depending on the language that you choose, you will have higher or lower level toys to play with, and you should know the toys in your language. If you're working with Java or if you're working with Python, make sure to know all the libraries, all the things that are provided by your language, and you know how to use them to construct the things and the algorithms that you usually need. Okay, so enough introduction. Let's start talking about range minimum queries. Now, the range minimum query problem states that you have a list of numbers and you want to find in this list the minimum within a given range. So let's say your list goes from 0 to n minus 1. You have a range a, b given, and you want to find the minimum value in this range. You may want to do this many times. You may want to change the numbers in between these queries. So depending on the type of task that you have, you can think of this as a static problem where the numbers are fixed, or a dynamic problem where the numbers are changing as you answer the queries. So in the static case, whenever you need to answer a query, say for the range AB, you just take the minimum over each value in the range AB one by one, and this range is, in the worst case scenario, as large as the whole list of numbers. So naively, you get O n answering of the queries, and so this is the time to answer the query. And in the dynamic case, you do the same. So again, you get O n answer, and changing each number is easy. You just find the position you want to change, and you just put the number here. So for changing, it's trivial, and you get O1 modifications. So this is the naive thing to do. Now the question is, can we do better than this? Let's start by the static case. So the range minimum query, when the list of numbers that we have underlying, that we are answering questions for, is static, never changes. So in this case, there's a trick that we can use that is usually known as sparse tables, which will allow us to answer any question, any type of range minimum query that we get in O1, so the optimal time that we can ever hope for. But there's a cost, which is a pre-processing step of O n log n, where n is the size of a string. And there's also a memory cost to store some extra data that will also be O n log n. So you see, this is much better. You don't have to take O n time to answer, and the cost that you pay, the price that you pay for this, is storing a bit more and doing a bit of pre-processing. The idea is very simple, and it's based on a property of the minimum function that tells us that, let's say we have our range A, B, and we want to compute the minimum over this range. Then we can take some subset of these elements and take the minimum, consider a different subset of these elements and take the minimum there, and the minimum over the whole interval, so the minimum in A b will be equal to the minimum of the left part and the minimum of the right part. Because the intervals that we have chosen cover the full range between both of them, and the function minimum has a property usually known as being one identical, which tells you that taking the minimum of an element many times, in this case these elements are taking the minimum over twice, it doesn't matter, the result is unaffected. The minimum of the whole range is the minimum no matter where it is found, either on the left, on the right, or on the middle, where both intervals overlap. How do we use this observation to compute the sparse tables? Well, let's say we have our n numbers, which are forming a sequence ni for I 0 to n minus 1. Then we define the sparse table of order k at position I as the minimum over the nj's such that j goes from I to I plus 2 to the k. And this is defined for I 0, 1, and so on up to n minus 2 to the k, and k 0, 1, and so on until essentially log in base 2 n. With this definition, we have that the sparse table of order k can be computed at position I with dynamic programming as the minimum of the sparse table of order k minus 1 at position I and the sparse table of order k minus 1 at position I plus 2k minus 1. Why is this so? Because if we have to compute the minimum over the elements at position I up to I plus 2 to the k, then the middle of that interval is I plus 2 to the k minus 1. The first part here computes the minimum there. The second part here is computed by the second term. Now, these two intervals don't overlap, and this is very nice, but when we answer queries, it won't always be the case. This is not a problem. Let's say, again, we have our sequence from 0 to n minus 1. We have to answer a query from A to B. Then we need to choose the largest k such that 2 to the k is smaller than the length of the interval, which is b minus a. Then, to cover the interval ab, we can choose a range starting at a of size 2 to the k and an interval ending at b of size 2 to the k. And we know, because we said that 2 to the k was smaller than the length of the interval b minus a, then 2 to the k plus 1 is larger than length, and these two intervals do overlap in a region here, so we are covering the whole range AB. In summary, the answer to a query in the range AB is, after we have performed the computation with dynamic programming, the minimum of the sparse table at position A of order k and the sparse table of order k at position b minus 2 to the k. the implementation is very simple, and we can immediately see that we have in the initialization a loop that goes over log n terms, another loop here that is O n. So, as we said before, the initialization is O n log n, and then we have here the queries, which are just looking up values in this table. This is O1. The only thing to keep in mind here, I'm using a compiler instruction to get the largest set bit of E minus S, which is in this case is the interval from S to E. So this gets the largest k such that 2 to the k is less than the length b minus a. Now, what do we do for the range minimum query problem when we have dynamic situations? That is to say, our numbers change with time. So let's assume that the sequence length does not change, but the sequence elements can change. The common solution for this type of situation, where you don't only need to answer queries, but also keep maintaining your data structure so that it can take updates of various elements in the sequence, is to use segment trees. So segment trees are binary trees that essentially have nodes which represent intervals of your sequence. So the highest node, the root, represents the full interval. Then it can have a left and a right node, and each of them will represent the left half. So this one represents the left half of the interval, whereas the right node represents the right half of the interval. Then you will have each of them with left and right nodes, and again, for example, the left node of the left red node here will represent the left half of the first left interval, and so on, right? So, for example, this guy here in yellow represents the left half of the right half. So it's this part there. This goes on until the leaf nodes have just size 1 intervals, so they represent a single element in this list of numbers. A very concise and elegant way to represent binary trees is to identify them by numbers. Then we can use that if you have a given node I, then the left child of this node is identified by 2 times I, and the right child of this node is represented by 2 times I plus 1. So we assign the root the number 1, then its left child is assigned the number 2, which in binary is 1, 0. The right child is assigned the number 3, which in binary is 1, 1. And this continues on. This is 4, 1, 0, 0. This is 5, 1, 0, 1. 3 has 6, 1, 1, 0. And 7, 1, 1, 1. In this way, what we get is that all our nodes can be represented as a list from 1, in this case, to 7, 2, 3, 4, 5, 6, 7. And the edges point like this, right? And so on. So from here you have an edge here. Now let us analyze this structure, this binary tree, how it needs to be created, updated, and how it is used to answer queries. First, let us analyze the number of nodes that we have on our tree. So there are n leaves because each of the leaves represents an interval of length 1, and we have n numbers. So n leaves, the level upstairs of the leaves has n over 2 nodes because each one represents 2 numbers. The next one has n over 4, and so on. This means the total number of nodes is n, which is a common factor outside, 1 over 2 to the k, where k goes from 0 to the logarithm of n, because the last level represents 2 to the log n numbers, which is just n numbers, the whole range. This is a geometric sum, so you get n times 2 minus 2 to the minus log n, right? Of course, this is nothing else than 2n minus 1, and this is of course O n. So we now know that we need O n memory to store each of the nodes in our binary tree. And what do we store? What value do we store in these nodes? Well, we said each node represents an interval. The natural thing is to store the value of the minimum in that interval. So the value at a given node is the minimum over all the elements in that range represented by that node, and this can be computed easily as the value of the left child and the value of the right child. So the minimum must be either on the left or on the right half intervals, with this initial condition that the value on a leaf is the minimum of an interval with just one element, is just the element that we had, the ni corresponding to that node. So now we have a better idea of how our tree is constructed. We have a root, we have left and right childs for every node, and we said each node represents an interval in a given range. We know how to compute the value of a node given its left and right values. So when we need to update this tree, what we do is we update values from the bottom to the top. So let's say we have 4 elements, we want to update this one. Well, we just change that value, then recompute the value of the parent, then recompute the value of the root. And if we had more levels, we would keep doing this. How many updates do we need to do? 1 per level. We said there are log n levels because each time you double the number of elements in your range. So the update is O log n. The initialization, I didn't mention it, but since we have O n nodes and we just need to initialize each of them, is O n, and we basically first initialize all the leaves, then all the nodes in the first level, and so on. This structure, the binary tree structure, clearly indicates that a nice implementation will be recursive. So you can do a non-recursive implementation. It might even be faster because you save some function calls, but in practice the shortest and cleanest implementation of all these methods are all recursive. So now that we have considered how to update and how to initialize the tree, the only thing remaining is to say how we answer the queries. what do we need to do? We have our interval. Let's say we are given the range A, B here. Then we can think of this interval as being constructed from pieces at different levels. In this case, to construct, let's say, the interval from these three nodes, there is one node representing this element, and we could choose this node and this node to represent the other two, but this would be inefficient because we have a higher level node that represents the full two elements. So this guy represents both. In general, it's not hard to convince yourself that you will need at most two nodes from each level, and therefore answering is about considering O log n nodes, in fact 2 log n because there are log n levels, and taking the minimum over all those elements. In an implementation, it is usually convenient to isolate the operation that you're performing, in this case taking the minimum, from the rest of the data structure, so that then the data structure becomes more general and you can use it with any other operation that you like that has the same properties. So this is also a way to identify the properties that the operation has that are important for this data structure to work. So you see here, I have defined the representation of the tree, left and right children. So this is very standard, but here I have defined a neutral element for the operation. What does this mean? So it means that if I take my operation with this neutral element, it will return whatever else I pass to it. In this case, the neutral element is basically plus infinity, a very large number, such that the minimum of any number and plus infinity is always the same number I give it. So this is how we define the neutral element. In practice, we don't have plus infinity in a computer, but we have a very large number, in this case the largest number that we can represent as an integer. And then the operation is isolated in a separate function here, which I call oper. This is just the operation that we are taking to merge two nodes into their parent node, as you see here. Then if you want to replace this operation, let's say if you want to answer range maximum queries, what you have to do is nothing else than replace this operation, change the min for the max, and change the neutral element for the neutral element for the max operation. In this case, it would be minus infinity. In any case, to initialize this implementation, what you would call is the initialization function with the root node, which is 1, the range of values that you want to represent, 0 to n, a pointer to the array where you have the nodes, and a pointer to the values, which I call m here as an array. To implement the update and querying operations, what you have to do is, for updating, choosing whether you need to update the left side or the right side of the binary tree according to the position that you are updating. Then, for queries, you need to consider the different cases. Either your interval is disjoint with the interval represented by this node. So the interval represented by this node in this code, it goes from start to end. The interval that you're querying goes from A to B. In this case, you have that the intersection of S, E, intersection A, B is the empty set, then you return the neutral element. If, on the other hand, the intersection that you have between the interval represented by this node and the target interval is just equal to the interval represented by this node, then the full value is what you need, and the final case here corresponds to a situation where the interval represented by this node and the target interval have a partial intersection. In this case, you just need to recursively call this operation on the left, on the right, and join them using your operation. So merge the results of the left and the right nodes. Now, I showed the implementation for the segment trees because I think it's important that you see specifically that we only need to define a neutral element and to define an operation for merging nodes. So as long as you can provide these two definitions, you can define a segment tree for whatever operation you want, whatever situation you have. In particular, so we saw for the operation, let's say comparison to less than, this is the mean, we had a neutral element that was essentially plus infinity. For the max, we had minus infinity. But it's very easy to think that, for example, we can use plus and the neutral element will be 0. We could use the product and the neutral element would be 1. We could use a binary operation, for example, XOR, and the neutral element would again be 0, and so on and so forth. So once you have the implementation for a generic operation with a neutral element, and this operation has a sensible way to join two results, then that's all you need. You have a data structure that will have O log n updates, and so this is for updating, and O log n queries. Now, let's move on to interval sums. I said just now that you can adapt the segment tree I just talked about by replacing the operation by the plus and replacing the neutral element by 0, and it will immediately give you a data structure for dynamically computing sums over intervals and updating certain elements. Now, the static case, you cannot adapt similarly the sparse tables, because if you have a range 0n and you have some interval where you want to sum AB, then choosing the left part and the right part, if they have some overlap and you sum both, you are overcounting the part I just colored in green. So while the dynamic case is immediately solved by segment trees, the static case is not the same. But for the static case, you probably know something that you may not even consider a data structure, but it is a data structure in a sense. The solution for the static case is the partial sum trick. So how do you work with partial sums? You define, let's say you have this list of numbers ni, you define partial sums si as the sum from 0 to I of the elements that you have, and then when you need to answer the sum from A to B of the Ni, you just write it as Sb minus Sa minus 1. Now, the key point here is that we are using a minus operation, which is the inverse operation to the sum. So if you add 2 and subtract 2, you get back your result. So in a sense, subtraction is the inverse operation to the sum. This is trivially easy to write in code, but I've written it in this way to make clearer the fact that this is in fact a data structure and it has an operation and it has its inverse operation here. If you look at this code, it's essentially the same as the code that we use to compute hashes. So in the lecture where we talk about hashing and rolling hashes for strings, we were using the partial sum trick for hashes, and we were relying on the fact that we had both an operation to add characters to a string and an operation to remove characters from a string. So because of that, we got the nice running time from this data structure, which is essentially O n initialization and O1 querying. But now that you know this, it also means that, for example, you can create a dynamic version of hashes by just implementing a segment tree, for example, with the operation combine hashes, and in the segment tree you don't even require to have an inverse. This procedure can actually be generalized to higher dimensions. So for example, if you have two axes x, y, and you want to sum over a rectangle here, which on x it goes from A to B, and on y it goes from C to D, to compute sums of elements in this range, you can compute partial sums. So define Sij as the sum from k equal to 0 up to I, and the sum of L equal to 0 up to j of your nij's, which are now bidimensional, and the answer to summing, let's say, from I equal to A to B, and for j equal to C to D of nij, can simply be computed as SBD with positive sign, SAD with negative sign, SBC with negative sign, and SAD with positive sign, where the first term computes all of these. So this is this guy. Then we have added too much, so we subtract this guy, which is AD. Then we also have added too much here, which we subtract there. And because we have subtracted twice this region, we have to add it back again there. Now you see this procedure, pre-computation requires O n square, because you have to compute these values which have two indices, and answering takes O1, so this is initialization, and this is querying. Of course, this generalizes higher in dimensions, so you can actually compute partial sums in any number of dimensions. But the problem is, as usual, you run into the curse of dimensionality. That means that initialization takes O n to the n, and querying is O 2 to the n. So here we have the curse of dimensionality. As we go up in dimensions, this becomes very quickly impractical. And here we need to use the inclusion exclusion principle. However, this is still something that you should keep in mind. Sometimes you have maybe a two-dimensional or three-dimensional problem, and you can still use partial sums in the same way. You just have to add the inclusion exclusion principle to add all the possible subsets of your parameters in each dimension with the correct sign. For the dynamic problem of computing interval sums, I already mentioned that you can use the segment trees that we discussed, but I still like to present a different solution which is more efficient, and it's called Fenwick trees or binary index trees. Very briefly, these trees are just a different way to organize the segments. So we saw that the segment tree basically divided the segment that we wanted to represent as one half on the left, one half on the right, and so on. Now, in a binary index tree, each position, let's say position I, will hold a number of elements, will hold the sum, or more generally, the operation that you want to perform applied to a given range of elements that depends on the binary representation of I. So, more precisely, we define that the binary indexed tree at position I will be the sum from j equal to I minus 2 to the k plus 1 up to I of the elements that we have in our array. And here k is the position of the first bit that is set in the binary representation of I. Then, to answer a query, what we need to do is take position I. Let's say we want to sum from j equal to 0 up to a given I, the nj's. Then the binary representation of I is telling us which intervals, which positions in our tree we need to sum. We just need to consider each of the bits that are set in I. So of course, because this is a binary representation of I, this is O log n intervals, and therefore the querying is just summing O log n things and takes O log n time. Finally, of course, what we can do to answer general queries from A to B is again use the fact that the operation has an inverse, and we can subtract the part of going up to the beginning of our interval. So I'm not going to go over the details of the implementation. I'm just showing here the code to show you that there's some tricks that you can play with binary operators to access and make sure that you move around these indices this binary index tree indices efficiently. And the whole point is that, again, we are using only the plus operation here. So you can replace this operation by any other operation that you want, that you know how to combine intervals, and you can use binary index trees in this way, replacing these 2 points. You can, of course, also go to higher dimensions, but you will again run into the curse of dimensionality. So you will again have an initialization that is O, the number of elements that you have, to the power of the dimension that you're working on. And this is going to be a problem as soon as you go further than, let's say, 2 or 3 dimensions. So, as you have seen, there are many different choices to answer queries on a range or on an interval in higher dimensions when you know your operation has an inverse. So in the static case, you could use the partial sums. In the dynamic case, you could use either segment trees or binary index trees. Now I want to discuss what happens when you have some generic operation that does not support an inverse. So no inverse. Now this complicates things. You cannot use partial sums, you cannot use Fenwick trees, but you may be able to use segment trees which did not require the inverse. However, there's a more natural choice in the static case, which is a generalization of the sparse tables. So let's say you have your list of elements n from 0 to n minus 1, and you want to compute some operation on a range a, b, and this operation is going to be some generic thing, na, and I denote it by a cross, na plus 1, cross, and so on until nb minus 1. Then the sparse table that we explained before at level k, starting at position I, was computing the operation, our general operation, starting from position I up to I plus 2 to the power k of the elements nj. With these sparse tables, what we can do is, instead of using just 2, if we don't have the one identity property that we can superpose the operation without affecting the result, then what we do is just we construct the range that we want with shorter and shorter segments. And again, we can use dynamic programming to compute the sparse table at position I of level k as the operation that we have performed on the sparse table at the previous level at position I, and the sparse table at the previous level at position I plus 2 to the k minus 1. The code for this is very simple. The initialization is essentially the same as it was before. It's still on log n, and the querying is what changed. Now this is O log n, because you have to go over the different bits in the length of your interval and perform the operation here on the result. So you have in this case the neutral element, the initial state of your operation. For generic operations in the dynamic case, you can always try to use segment trees, but sometimes you run into trouble, for example, when you don't know how to merge large chunks or segments of your data. So, as we said, you have in a segment tree nodes representing intervals, so this represents the left and this represents the right, the node on top represents the full thing, where you've combined left and right. So you need to be able to join two intervals into one, and sometimes this operation is non-trivial. In this case, a nice data structure, a nice trick that can be used is, instead of representing your whole range by this binary tree, you just take a given number of cuts in your data, and then you just keep manually track of the result, let's call it the result, in each of these segments. So the best way to do this is to actually cut the interval, if it has length n, into O square root of n cuts. Each will have then square root of n elements. Therefore, you get square root of n updates, because whenever you change an element, you have to update the result stored for the whole cut of your where it belongs, and you also have O square root of n queries, because you can sum each of the segments that belongs to a given range, and you can sum or operate actually on the rest, right? So if you want to answer, let's say, something like this, you sum the full result here and here, and then you add manually the little parts at the ends. This is useful when you do not have this possibility of joining large segments, and as I said, the query then is O square root of n, and the update is also O square root of n. So you see, you have another option for a dynamic data structure that works for generic operations. In this case, you don't need an inverse, and in this case, you don't even need to know how to merge more than one element at a time into your results. In summary, what I want to stress is that all during this lecture, what we've been doing is analyzing operations, analyzing queries that we need to perform and functions that we need to implement in our data structure, and analyzing the properties of the operations that our data has. So, for example, whenever you're dealt a problem where you want to apply a data structure, you should start by asking whether this is a static or dynamic case, right? You also want to analyze whether your operation has an inverse. So if the operation that you want to apply has an inverse, you can use things like partial sums, otherwise you cannot. You may also want to analyze whether it has this property, like the minimum function, one identity, that you can apply, let's say, the operation in overlapping segments, and this doesn't affect the result. You can also figure out what the neutral element is, which you will need in different points in your implementation, and so on. So all of these questions that are here should lead you to the best choice of data structure for your current problem. So the data structure depends on all these things and on the running time that you want to achieve. So sometimes the naive algorithm just works, but if you want to achieve a given running time for a certain operation that has certain properties, you need to choose the right data structure. I think it's very useful to think in this way, a bit abstractly, about the operations that you're performing, and not just keep in mind that you have a sparse table or a segment tree that just computes sums. So these are very generic tools that allow you to do many different things, not just the one thing that may be pre-implemented in your notebook just because this is the first thing, the first example that comes to mind. That being said, you can think of a lot of improvements to the data structures that I've talked about. So I'm just going to mention two that are, well, they may be well known, but they are a bit more advanced than the standard thing that you find in all discussions of segment trees. So these are two modifications of a segment tree. The first one is about laziness. So how to postpone operations that you don't want to move down the tree as they are done. So in a segment tree, we said we have nodes representing intervals, and the whole point was that to update, you update a position, and that means updating from the leaf all the way up to the root, so following this path. Now, what if you want to update a whole range, let's say this range? You would need to update many positions, and this update would take O n time in general. In fact, O n log n, because for each time you would be going up. However, in fact, you don't need to update all the nodes if many of them are contained in same interval. So in this case, I can avoid updating this guy and this guy by just realizing that updating their parent is already enough. Now, in order for this to work, I have to do two things. So first, I need to make sure that I know how to update a whole range. So updating ranges needs to be an option. So for example, if the update is sum a given number to each element in this range, then I can just sum to the full result of the range n times that number, where n is the length of the interval. So updating ranges is one of the conditions that I need to satisfy. I need to know how to do this. The other condition is I need to know how to split this operation when later maybe I need to then update something like this. So if later I need to update this position, it means that whatever I held here and I did not update the leaf will need to go down later, and as I update the next one, I also bring down the update I never did before. So this is the laziness part. You only move down the tree when you are forced to by some update query that is trying to get to a particular leaf. So this is the laziness part. You need to be able to break or separate operations that we have postponed for later. So this technique is very general. It applies to many data structures. I'm just showing it here for segment trees because it's very clear in this case how each node can push down an update or can stop pushing down that update if it can do it all by itself. So if your operation supports these two conditions, then you can update ranges and you can improve your data structure by not just updating a single element, but updating a whole range. Finally, I want to mention also persistence, which is something that comes useful when we have dynamic data structures that basically change the underlying data. Now, let's say again, for the sake of example, we have a segment tree. Of course, persistence can be applied, at least the idea, to many other data structures. But the whole point is that when you update your data structure, you just lose the one you had before. So you lose the ability to query your data from before. But what if you want to update the data and answer queries about any state of the data during any of the times that you've updated? So initially you have your range represented by a segment tree. Then when you change some element, you would like to have a different segment tree to answer queries either about the black data or the red data. However, if you just use a normal segment tree, the nodes will change and they will forget something about the old data. You can still solve this problem by realizing that the trees are almost identical. They share all the nodes except the ones that lead to the leaf that is being modified. So instead of just updating values, you can create new nodes. So you create a new node, in this case red, which has a right child that points to an old node because that node did not change, and its left child will point to a new node because the left child changed. Then again, the left child of the new node will point to an old node because the left child did not change, and this guy will point to a new red node. So here I'm assuming that this position goes there, this position goes there, this one goes there, and this one goes there. Then when you need to query, you can either query the black tree or the red tree, and you will be querying two different sets of data. As you make more changes, let's say next you change this position, you can again create a new root. Then in this case, this root will have its left node unchanged, the right node will be a new node, then again the left node gets unchanged, the right node gets a new node, and this will point to the new data. So now you have an axis of time. So this is the time, and when you query, you can query your data at any time from the beginning, the first original data that you had, until the end when you've done many modifications. The key point here is that each update takes O log n time, because you're just adding nodes in one level at a time, and it also takes O log n memory. So both in time and memory you have O log n, which is pretty good, and this will be very useful when you have an axis of time in your queries and you want to query at different times. Or sometimes you have problems where you will find that introducing some artificial time, let's say thinking that the actions that are performed on your data happen along some time, you can then realize that the problem is solved by asking questions about the past. Okay, so I hope that this lecture has helped you maybe organize and bring together different data structures that maybe you knew before, maybe you didn't, but the whole point is I think you need to look at them as a whole, as a set of tools that you have and that you can adapt according to the different problems and the different properties that you are dealing with. So as usual, if you have any questions, I'm happy to answer. And also I encourage you to go and try these things by yourself. So I showed code for some of the more basic things that I talked about, but you should try to implement the other stuff, the one I did not show. So I did not show code for persistence, I did not show code for lazy data structures. It's a nice exercise to go over the data structures that you already know, that you already have implemented, and try to add properties, try to add functionality, adding layers. For example, you can add laziness, you can add persistence, and it's nice if you can get these to be more or less generic. So if you can add a laziness layer and a persistence layer, and they are pretty generic in the sense that they adapt to different data structures, different operations, different properties, you will see that you will now have a very, very complete set of tools that you can just choose to use whenever you have a complex problem with many different moving parts.